In the vast, silent theater of space, a stranger entered our solar system. It came fast, without a sound, its origins a complete mystery. This is the story of 3IATLAS, an object that crossed the immense void between the stars to visit our cosmic neighborhood. Our journey begins on a dark night, under a star field so dense it feels like spilled diamonds. From within the silhouette of an observatory dome, a telescope awakens. It slews across the sky, a silent hunter in the dark, its mission to capture the faint whispers of light from distant worlds. Tonight, it's hunting for something new, something that doesn't belong. Photons, particles of light that have traveled for millions, perhaps billions of years, finally end their journey on its sensitive detector. Then we see it. The first photometry reveals a barely perceptible streak against the black canvas of space. It's faint, elusive, just a ghost of a visitor passing through. This is our first glimpse of 3IATLAS. What is it? A comet? An asteroid? Or something else entirely? To find out, we need to analyze its light. The early optical spectrum gives us our first real clue. It shows a distinct red slope, meaning the object reflects more red light than blue. This is common for bodies in our own solar system, often indicating a surface rich in organic compounds, the building blocks of life. But this traveler isn't from around here. As we look closer at the spectrum, we notice what's missing. There are no strong signs of the typical gases we see from active comets, like cyanide or diatomic carbon. This suggests the object is dormant, a silent, icy nucleus coasting through space. We can imagine it now, a dark, reddish rock tumbling through the darkness, its secrets locked away beneath a frozen crust. For countless millennia, this object has been adrift in interstellar space, bombarded relentlessly by high-energy cosmic rays. This cosmic radiation would have profoundly changed its surface, baking the outer layers and transforming simple ices and organics into more complex, darker materials. This process, called space weathering, creates a sort of protective shield, a mantle that hides what lies beneath. Back at the telescope, astronomers notice something subtle. The reddish slope of the spectrum isn't perfectly constant. There are tiny variations, hints that the surface isn't uniform. Are we seeing patches of different materials? Or could this be a sign of something stirring deep inside? Answering these questions requires more than one pair of eyes. A global network of telescopes swings into action. From the SOAR telescope in Chile to the powerful Very Large Telescope Array, astronomers around the world coordinate their observations, all pointed at this one enigmatic speck of light. This massive effort is our best chance to unravel the story of 3IATLAS before it disappears back into the interstellar night. As the data floods in, the first light curve begins to take shape. A light curve tracks an object's brightness over time, and for 3IATLAS, it reveals small but regular variations. The object gets slightly brighter, then dimmer, then brighter again in a predictable pattern. These subtle pulses of light are the key. This rhythmic change in brightness tells us something fundamental. The object is rotating. Like a lopsided potato spinning in space, its irregular shape reflects different amounts of sunlight towards us as it turns. By measuring the time between the peaks and dips in brightness, we can calculate its rotation period, the length of its day. But there's more. The color, or the steepness of the red continuum slope, also appears to change in sync with its rotation. This is a huge clue. It means that as the nucleus spins, we're not just seeing a change in shape, but a change in the composition of the surface we're looking at. One side might be slightly different from the other. Perhaps one hemisphere was more exposed to the harshness of interstellar space. Or maybe, just maybe, one side is beginning to wake up. We can imagine it now. As one face of the nucleus turns towards the distant sun, its surface warms ever so slightly. Could this be enough to cause a tiny amount of gas or dust to escape? A fleeting puff of activity too faint to be seen directly, but just enough to alter the light we receive? The cosmic, ray-battered crust might be hiding pockets of pristine, volatile ices deep within. These are the primordial materials from its home star system, preserved for eons. A storm may be hiding just beneath the crust, a reservoir of frozen gases waiting for the right moment to burst forth. For now, the visitor remains quiet. The first week of observations gives us a tantalizing picture, a rotating, reddish nucleus, showing hints of a complex and perhaps active inner life. As we watch the time-lapse of that first week, the object's brightness rising and falling with a steady rhythm, it feels like we're listening to a whisper from across the galaxy. The comet whispered, but did not speak. Now we enter the second week of our watch. The light curve continues its rhythmic dance, day after day. We see the rotational modulation clearly now, a consistent pattern of peaks and dips. Annotations on the graph highlight each maximum and minimum confirmed by different telescopes around the world, proving this is a real signal from the object itself, not an instrumental error. We can visualize the nucleus tumbling through space, its elongated, irregular form catching the sunlight. One moment we see its broadside, reflecting a maximum amount of light back to Earth. Hours later, it rotates to show us a narrower end, and its brightness dips. This celestial ballet, happening hundreds of millions of kilometers away, is painted in the data right before our eyes. The variations in its color, the continuum slope, also persist, growing more defined. The link to its rotation is undeniable. As certain regions of the nucleus spin into view, the light it reflects becomes slightly redder or slightly less red. This strongly suggests that a faint, almost invisible activity is beginning. The sun's warmth is starting to stir the ancient volatiles trapped beneath the surface, causing subtle changes that our instruments can just barely detect. The silent visitor is starting to mumble. The story is just as we refined our understanding of the comet's rotation, a fascinating pattern emerged from its light curve, the regular brightening and dimming as it spun. We could see the comet wasn't just a passive traveler, it was alive with activity. Animations showed dust and volatile gases being released from its surface, not randomly, but in bursts. We discovered a direct correlation between its rotation and these sudden outbursts of activity. It was like clockwork. As certain regions of the nucleus faced the sun, they would erupt, spewing material into space. Plotting the comet's spectral evolution over time revealed even more. We could see the chemical makeup of its coma changing, moment by moment. It was as if the comet's internal clock was revealing its secrets. This wasn't a one-telescope job. It required a coordinated effort, combining data from observatories around the world. By overlaying photometric data with these spectral time series, the picture became crystal clear. The comet was breathing, exhaling its ancient materials in a rhythm dictated by its spin. We saw how cosmic rays had altered its surface chemistry over its long journey through interstellar space. The ratio of dust to gas wasn't constant, it shifted precisely with each rotation. As we looked closer, faint emission lines began to emerge from the noise in the data, hinting at rarer molecules waking from their long slumber. The hidden story continued to unfold. Artist impressions helped us visualize what was happening, distinct layers within the nucleus, each contributing to the outgassing we observed. Every peak in the light curve was now synced perfectly with a visual of the comet's spin, confirming our theories. But where did 3IATLAS come from? This was the ultimate question. We shifted our focus from the comet itself to the vast star field of the Milky Way, searching for its home. Using data from the Gaia Space Observatory, we mapped millions of stars in 3D, each one a potential witness to the comet's birth. Our computers began the colossal task of integrating the comet's trajectory backward in time, rewinding its journey through the galaxy. Each star was a suspect, every motion a clue. We zoomed in on the most likely candidate stars, examining their past movements, but one by one, they were ruled out. No star within the limits of our search could be pinpointed as the origin. The mystery deepened. We were left with a three-dimensional map of interstellar space, with the comet's path traced back millions of years, leading nowhere. It was a cosmic cold case. We could imagine the comet traveling for eons, its parent system lost to time. The parent system vanished into the void. We explored multiple possible trajectories, but none led to a conclusive answer. It was like cosmic detective work, searching the starfield for witnesses that weren't there. We watched the Gaia data in reverse, stars moving back to their ancient positions, but still no match. The birthplace remains a mystery, a secret carried across light years. The animation showed the comet's path, perhaps originating from far outside the plane of our own Milky Way galaxy. We created timelines of possible stellar encounters, only to eliminate them all. In the end, we were left with a humbling image: the comet. A tiny, lonely streak of light among billions of stars. 3IATLAS spoke to us through its light and motion, but its origin remains hidden in the cosmos. We begin with a simulation of its rotational axis, a slow, steady spin in the vastness of space. Watch closely as we model its three-dimensional orientation. At first glance, everything seems calm, but look again. Faint, almost imperceptible dust emissions begin to appear. Each tiny fluctuation in brightness is a clue, a breadcrumb, leading us toward a bigger picture. When we overlay its light curve, the graph of its brightness over time, with its spectrum, a pattern starts to emerge. Even minor spikes in brightness hint at an early rotational signature. We can even visualize subtle interactions with cosmic rays, painting an invisible picture on its surface. A close-up reveals the faintest hints of emission, signatures of cyanogen and nickel. By comparing photometric data from multiple telescopes, we notice subtle changes in the organic compounds visible in its continuum. The hidden story is just beginning to unfold. Our artist's impression shows the first delicate layers of dust being gently released from the surface. The stage is set. As we enter the second week, the clues become more pronounced. Our time-lapse animation of its spectra shows a dynamic, evolving story. We now have a confirmed detection of those minor cyanogen and nickel emissions we suspected earlier. Notice how the continuum slope evolves, a key indicator of changes on its surface. We'll highlight these faint emission lines so you can see them clearly. When we overlay the rotational phase with these spectral variations, the connection becomes undeniable. The object's spin is directly influencing what we see. Our artist's impression now shows the first embryonic dust jets beginning to form. The surface may still appear calm, but deep within, interior secrets are stirring. By overlaying data from multiple telescopes, combining spectra and light curves, we can track fluctuations in the line flux with incredible precision. A new animation shows the dust coma, the atmosphere of dust around the object, beginning a subtle expansion. We refine our understanding of its rotational modulation. It's like being a scientist, examining these anomalies, knowing they're pieces of a larger puzzle. Faint variations in the spectral slope hint at the presence of complex organic molecules. Let's pause for a moment. A suspenseful beat as the object, once a simple point of light, slowly reveals its true nature. Our artist's impression now shows faint jets becoming visible on its rotating nucleus. By the third week, the activity truly begins to ramp up. The brightness spikes we saw earlier are now more frequent and intense. We can plot the dust-to-gas ratio, a critical factor in understanding what's driving this change. Visualizing the correlation between its rotation and its activity reveals a direct link. As the object spins, it exposes different regions to the sun, triggering these outbursts. Our animation shows the dust coma expanding more rapidly now. Overlaying the spectra with the photometry gives us a multi-layered view of the event. Each flicker of light is a clue. Our artist's impression captures these faint but now distinct dust jets. We can see how the orientation of its rotational axis affects the brightness we observe from Earth. An animation of the emission line variations shows just how dynamic the surface has become. Coordinating the timelines from multiple telescopes allows us to build a comprehensive picture. We can even visualize how cosmic rays might be influencing the surface chemistry, creating the very compounds we're now detecting. The rotational phase is clearly controlling the activity. Time is the detective's ally. Combining the light curve and spectra into a single visualization, we see the full story. But the calm is deceptive. A final artist's impression takes us beneath the surface, revealing layers within the nucleus, with pockets of dust ready to be released. The peaks in its light curve now sync perfectly with its rotation. As we move into the fourth week, the activity escalates. We're witnessing a full-blown awakening. Analyzing the brightness variations allows us to precisely map the active regions on the nucleus. The dust-to-gas ratio is now a key focus, helping us understand the composition of the material being ejected. Our animation shows the dust jets growing stronger, more defined. The connection between rotation and activity is undeniable. When we overlay the photometry with the spectra, we can pinpoint the exact moments of outburst and see their chemical signature. These are not random events. They are governed by the physics of a rotating, heating body. Let's pause and appreciate this moment. The story of a billion-year-old object is being written in light, right before our eyes. Our artist's impression now shows powerful, collimated jets erupting from the surface. We can even simulate the complex three-dimensional structure of these jets. By tracking the emission line flux, we measure the amount of gas being released, watching it fluctuate with each rotation. Coordinating data from our global network of telescopes gives us an uninterrupted 24/7 view. The dance between cosmic rays and surface chemistry continues, a silent engine of creation. The object's rotational phase acts like a switch, turning activity on and off as it spins. The mystery is unraveling. The combined data streams paint a complete picture. A final pause. The quiet wanderer has revealed itself to be a dynamic, active world. Our final artist's impression is a breathtaking view of the fully active nucleus, a testament to the power hidden within these ancient travelers. The clues have led us here to a deeper understanding of our solar system's origins. Thank you for joining us on this incredible investigation. The universe is full of mysteries, and with each observation, we get one step closer to solving them. If you enjoyed this journey, be sure to like, subscribe, and hit that notification bell so you don't miss our next cosmic adventure. See you next time.